How difficult would it be if there was a fault thrown in? Like a normal or a reverse fault. Something to ponder. Okay, thank you. Now, what we have done so far in the class is we've really done descriptive structural geology. We've looked at some of the geometries. We've tried to come up with various forms of classification and try to understand the basic geometries in these systems. If you recall, we started off with basic concepts, depositional features. What are the primary depositional features? How does that give us Younging? Look at basic principles like horizontality, superposition, cross-cutting relationships. And we ended up with geologic time. Then we looked at fractures, fracture systems, what we can learn from fractures and what some of the significance of fractures are. We looked at faults and fault systems, and we looked at a little bit of detail trying to understand the history of development of ideas, trying to understand the geometries, and a little bit about how the behavior of the lithosphere might impact the actual shapes, geometries, structures that we find. We briefly touched on folds. You can spend a lifetime on folds and still end up more confused than when you began. So we just touched on folds, and we very, very briefly touched on fabrics and metamorphic systems. What we want to do now is step away from the purely geometric. We want to begin to try to understand how do these systems actually behave? How do they form? Because if you recall from the beginning of class, we wrote this equation that stress causes strain. And so we need to begin to understand what this really means. We're going to end up saying that this is a second order tensor. Here using Einsteinian or initial notation here. This is going to end up being, and then this is going to be a larger matrix in that system. And so we need to begin to understand what does this actually describe. Now, some of this may be review. If you've had statics, dynamics, if you remember some of these basics, this may be boring. If not, we'll try to go through at a relatively easy pace, because it's critical that we really understand what we're talking about when we are working with these. Now, as in most textbooks, the chapters dealing with stress and strain are quite limited. And at least when I read them, I actually find it a rather difficult read, because they're trying to skip forward so quickly that you tend to get lost. And so some supplementary books that I rely on, this one for geology, stress, and deformation. This is a book written by Gerhard Ertl. It was an excellent, excellent reference book. Really, he gets into how do we use tensors in geology. So we're going to have to try to understand what a tensor really is in that system. This is a wonderful reference. An even better reference is this book by Pollard and Fletcher, Fundamentals of Structural Geology. This one is a fantastic book to read and use as a reference point. The only downside is at the time they wrote this book, they were really fascinated by differential geometry. And so apparently one of them had sat in on a class, a graduate level class in differential geometry, and thought it was the coolest thing in the world. And so they go a little bit overboard with differential geometry. But that sort of stuff's pretty straightforward anyway. So this is an excellent reference book. And if you are more of an engineering brain, this one, Introduction to Continuum Mechanics. There's several different books out on continuum mechanics. I like this one. This one is a really easy read something that you can polish off in a weekend. So if you need to review, this one is a great book. It has some really cool problems, some problems that are stumpers in here that will make you think and give you a headache from time to time. So we will draw on those sorts of materials as we progress through the book, or as we progress through these sections, beginning with stress. Now, in order to understand stress, and you would contend that since you're enrolled at TU, you know everything there is about stress. We're going to try to describe it and quantify it a little bit differently. What we're going to try to understand is, how do materials respond to loads? Can we begin to describe the stress fields that will develop in a material, assuming certain things about the material that has some sort of a surface load on the body? So we want to start off relatively simple. We're going to keep things in terms of the continuum. And I know that is perhaps not the perfect description, particularly for structures that we see geologically, but we're going to assume that we have a continuous material. Simply continuous. It has continuity. Any variations are going to be smooth, differentially smooth. We're not going to see any great breaks in the behavior of the material. So we're going to treat it from a relatively simple viewpoint. Discontinuum mechanics just gets weird. So we're not going to go into that domain. Now, first thing we want to do is have some general ideas of what we mean when we're describing a material. We want to have some basis of mathematics that we can refer back to. And if you go into the Harvey course, there are some background handouts, if you will, on scalars, scalar systems, simple vectors, vector systems, and tensors. And so if you would read through those and let me know where things go from, oh, that's obvious, to what are you talking about, so that we have a basis to know where we are in that particular system. And we're going to start here relatively simple. When we describe materials, especially when we describe materials geologically and describe geologic systems, we tend to use words like homogeneous, isotropic, or a system that is inhomogeneous or anisotropic. Those will have different meanings to different people. And so when we describe a homogeneous material, what is that? What do we mean by something that is homogeneous? Same property, same temperature, same composition throughout the system. And so we have a uniform, and I'm just going to call it character, where that character is, where that character might be something like temperature. I can have a homogeneous temperature in a system where the temperature at every point that I measure, let's pretend we're in a material body here, everywhere I go, I take my thermostat or my thermocouple with me, and I go, okay, same temperature everywhere. No variance, no gradient in this particular system. So I have a uniform character. That might be composition. If I have a quartz crystal and I'm able to shrink down and go into the quartz crystal, then I would be able to a certain scale, we have to be careful of scale, I would always see silicon and oxygen. Quartz, 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 everywhere we go. So the same uniform character. If it is inhomogeneous, then we have a variable. Character. And so if we look at the temperature field, let's say we try to treat Keplinger as a nice uniform material body. And with your experience, is the temperature homogeneous or inhomogeneous? It's inhomogeneous, or you could call it heterogeneous. We have quite a variance of temperature in the building at any given time. That's because of our great air handling system. And so when we look at the composition, when we look at the temperature field, we're going to describe this as a value at a point, independent of any coordinate system. We're not worried about a coordinate system, at least right now. This is a purely scalar entity. So we can describe this as scalar in nature. It's just a value. If we wanted to, we could have a value at a point, a value at some coordinate system, or we could just treat it as a scalar entity, scalar quantity. Now, when we describe a material as being isotropic, what do we mean? If a material is isotropic, what is it? Same response, same behavior in each direction. So here we have a response, a uniform so something that is isotropic will have a uniform response in each direction. Here we might want to superimpose some sort of coordinate system. Now, if you've been through the calculus sequence, and don't tell the math faculty that I'm teasing them, the math faculty gets all caught up in coordinate systems. You know, there's got to be right-handed coordinate system, it's got to be a left-handed coordinate system. Z always has to be up, or always has to be out of the board. In our perspective, in the geosciences, it doesn't matter. You can map. I can take this coordinate system and I can map it into a spherical coordinate system very, very easily. I can map it into an elliptical coordinate system. I can map it into an irregular curvilinear coordinate system. It doesn't matter. I can map back and forth between coordinate systems. My individual values may change, but I have invariants that are not going to change. And so we're not going to get caught up terribly in coordinate systems. We're just going to assume some coordinate system. I like this coordinate system just because I'm right-handed. So, and you can, you know, we can get into an argument now. Is this Z or is this Y? Or is that Z? Or Y?
This is Z.
Yeah, yeah.
Physics.
Doesn't matter, because you can map it back and forth. So we're going to play a little bit loose with our coordinate systems, and you'll just have to bear with an old person here. You'll just assume that, you know, maybe my wheelchair wasn't working quite right today, so I forgot which coordinate system we were working on. So an isotropic material, we have the same response in any direction. So if you're in mineralogy, if you're looking at a microscope and you have a material that is cubic, you have an isotropic material, you turn the cross nickels, what happens? It's black, it goes extinct in that system. So garnet would be isotropic. So in this particular case, any way I look, if I have some sort of a probe, I have an Acme toughness gauge, and I can come into the material and poke it this direction, I get some value. I poke that way, I get some value. I poke that way, I get some value, and they're the same. When the material is anisotropic, then we have differing response relative to direction. And so, you know, a classic example would be if we had a piece of wood. So if we take one of these mini podia here, would this be isotropic or anisotropic? Anisotropic, because the behavior of the material is directionally dependent. If we were to have a single piece of wood and we tried to break it like this, so we're all taking a karate class, Karate 101, and our master says, okay, now break the board. And he gives it to you this way. What are you going to do? Run, because it's going to hurt. You can't easily break it this way. So depending on the orientation of the object or the orientation of whatever force you're using, you get a different response. Wood is very, very anisotropic. Certain types of geologic materials are going to be very anisotropic. We think about a muscovite. Muscovites have an 001 basal plane that's very easy to split apart. Other directions, muscovite's actually relatively strong in that system. So they will respond differently depending on direction. Now, here's where it can get a little bit hard. If we were to go to a granitic outcrop, would you describe it as homogeneous or inhomogeneous? The granite. And a granite, if you recall, is going to contain a little bit of quartz, some feldspar. Sometimes it's going to be two feldspar system, maybe a touch of muscovite. Occasionally you can even find a biotite in there. Maybe you're going to find a little bit of hematite, maybe some weird ilmenites in there as well. Occasionally a zircon, occasionally an epidote. Is that homogeneous or inhomogeneous? Well, the correct answer is yes. It's going to depend on the scale of observation. If you are looking at the outcrop from a distance, and you look around, you're just going to say granite, 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 depending on how much of the material you're looking at. If you get down to the crystalline scale, you're going to say it is incredibly inhomogeneous. So it's going to depend on scale. Typically, when we're dealing with loads, we're going to treat granite as relatively homogeneous. We're also going to treat it as relatively isotropic. When in fact, when we're down at the crystalline scale, it can be incredibly anisotropic. So it is going to be, for us, scale dependent. What scale are we thinking about? But for us, we're going to tend to treat materials as homogeneous unless otherwise proven inhomogeneous. So innocent until proven guilty. And we're going to treat them as isotropic until we are forced, kicking and screaming, to treat it as being anisotropic in the system. And we're going to use what you may consider to be a cop-out rule, and that is the idea of a hand sample. if you have a hand sample of the material, is it largely isotropic or anisotropic on that plane of observation or that scale of observation? Is it relatively homogeneous or relatively inhomogeneous? And we can always make sort of an odd conclusion. Let's say that we have a granitic outcrop here that's fractured like this, and we want to understand the stress system. Would you say that's homogeneous? This is a trick question. Homogeneous or inhomogeneous? Isotropic or anisotropic? Yes. We would go in and say, look, if I pick that up right there, it's homogeneous and it is isotropic, depending on the scale that we are using. We do that simply to try, not that geologists are successful, but we try to maintain our sanity that way, just to be able to treat the system using the more simple description. Now, before we can really get into stress, we need to review some simple physics. So what we want to do is try to understand forces. Are there any rules by which forces must play? So we want to ask, are there any rules? By the way, what's a force? What are we going to consider to be a force?
Weight per area.
Pressure over a given area.
Okay. Let's be a little bit more simple. If I want to do something like this, I'm going to place this book on the table and I want it to move from there to there. What do I have to do? Do I have to do a Gagarin and think about it and cause it to move mentally? Can I? Yeah, it would take a while. So I'm looking at some action that is being applied, and we have action that is a surface type of action. We also have action at a distance. Now, if I have this and I let go, what's going to happen? Is it going to stay there? No. What happened? Gravity. Is gravity a force? Okay. What type? Was there some
Downward force?
displacive, downward? Do I have some sort of string that this is attached to that pulls it down?
Magnetic.
It's an invisible string.
Okay, it's an invisible string. What about body force?
Yeah, I was gonna say the weight already.
Okay, so we have different types of forces. We're going to generally talk about surface force, where you have to have some contact, and body force. Body force, a good example of a body force would be gravity. Action at a distance. Now, these two are different. If I'm going to cause that book to move, I have to have a surface force in that system. Here, if I drop this, that is a body force. That is an action at a distance. But are there any rules by which these forces have to behave? And I'll ask you maybe a bizarre question. Is gravity, do you have to have contact in order to have gravity, so that I have to walk very carefully to always make sure that I have my foot down fully? Otherwise I go flinging off? No. So no need for any sort of surface contact in that system. What are the rules? Well, have you heard the expression F equals ma? What does it mean? Okay, so what does that mean?
Weight versus where it's going and what distance per second squared.
Okay, but what does it mean?
The object will remain like
Will remain equilibrium unless it's subject to acceleration.
If I want to change the velocity of an object, what do I have to do?
Change the direction.
I have to apply force. And it's proportional. My change in velocity, I could just as easily have written dv dt here. If I want to change my velocity, I have to apply a force. And it's proportional to the mass. The amount of change of velocity is going to be proportional to the force that I apply and to the mass. So if I have a very large mass and I want to change its velocity by a certain amount, I would have to apply quite a bit of force. Okay? Are there any other rules here that are going to govern the behavior? Let's call this one momentum. Are there any other rules? Well, we're going to be in the world of physics, so we're perfect frictionless systems. We're not going to worry about friction in this one. What about inertia? What do we mean by inertia?
No, object's resistance to change in motion.
Yeah, a body at rest will tend to stay at rest unless it is disturbed. That's what alarm clocks are for, right? So if I have a body in uniform motion, it will remain in uniform motion unless we apply some sort of force. Then we think about it in terms of momentum in that system. Now, what if we ran an experiment? Can we demonstrate inertia? What's going to happen to those if I move this table?
You don't want to stay in the same spot.
They rolled this way when I was pushing that way. If I had an aquarium full of water or a coffee cup full of water, push the table, which way would the water go? It wants to stay at rest in that system. When we're dealing with geologic systems, we are concerned about inertia. We are concerned about the momentum of a system. And we also want to think about equilibrium. What is equilibrium? And you can write it, you can formalize it as the sum of the forces in the x direction are equal to 0. Sum of the forces in the y direction are equal to 0. What does it mean? If we were to apply an English phrase, you've heard the phrase that for every action, there is an equal and opposite reaction. If we say the sum of the forces in the x direction are 0, what does that mean? Could we demonstrate it? Well, we do, all the time. If we take a simple thought, I'm going to push on this wall. Is this wall pushing back on me?
Yes.
Is it equal?
No.
I hope so. What sort of world would this be like if I pushed on the wall and it pushed back one order of magnitude more than I applied? That would be very strange. Or the same thing if I'm walking. So I'm going to apply and the floor pushes back 10 times. So every time you take a step, that'd be a very, very strange world to be. And so what this describes is that in our system, we have some very, very simple rules. Momentum, if we want to change the velocity in a system, we have to apply a force. Inertia and equilibrium. And I know all of you are too young to remember all of the missions of the Gemini series, the Apollo series, the Mercury series, leading up to the landing on the moon. The first spacewalk, astronauts, incredibly well-educated, very sophisticated, very intelligent people, the first astronaut to try to do a spacewalk nearly died because they were struggling so much that their heart rate got out of control. They fogged up their visor, they lost orientation, they almost didn't make it back to the space capsule because they forgot their basic physics. The first astronaut to remember the basic physics was actually a physicist, Buzz Aldrin, who was working with a task and suddenly was struggling with it, suddenly realized, wait a minute, inertia, momentum. So this is how we're going to operate. We have to be cognizant of these as well in geology. And we're going to start with a very simple concept of a traction. And we're going to define it as some force acting on some area. And then we will go forward from there. And so next time, today's Wednesday, on Friday, we will do weird things like what is the traction at the base of a lithospheric plate. And work through simple concepts like that. Okay, I will be here today till noon.